Hey students, in this video we're going to talk about limits and continuity. All right, so a function is for the limit to exist at a point. It's going to be kind of like what we did in Cal 1. The easiest way to do this is to directly substitute the point into the function, and if we run into that indeterminate form of 0 over 0, we have other things to worry about. We're also going to talk about continuity. So let's get started. All right, so for example, when we have to find the limit for this function when the point x, y, some arbitrary point, is approaching the point 1, 2. So as I said, the easiest way to find the limit is to just substitute in the value. So as long as we don't divide by 0, take the even root of a negative value, we're good. So in this case, we can substitute in 1 and 2 without any problem. So that's actually just going to be 1 squared plus 2 squared, which is obviously 5. So that limit is 5. Very easy. For our second example, kind of the same thing. We can just substitute the point in directly without any problem, even though we do have a rational function. Because we have two things that are squared, as long as both of them are not 0 at the same time, we don't actually have any problem. So we can substitute in the point 1, negative 1. So we would get 2 times 1 squared minus 3 times negative 1 squared divided by 1 squared plus 2 times negative 1 squared. So that's going to give us 2 minus 3 over 1 plus 2, which is negative 1/3. So that limit is negative 1/3. So far, so good. Again, the easiest way to evaluate a limit is direct substitution. So we'll talk more about this in class and where we can like draw some examples of a boundary point. But for the purposes of us doing limits, consider a boundary point to be a point that is the extremes of a closed region. So like if I draw a circle, for instance, now a circle really is all of the points interior to something, but they're a fixed distance away. So the circle is the interior part. The exterior of the circle, or the part that we actually generally consider the circle, is actually the circumference. So like a boundary point is a point that's like just on somewhere on the circumference of the circle. So all these points around here make something a boundary point. And you know, we can get in the weeds right now. So for something to be a boundary point, it has to be true that, because in R2, when you approach a point, you're not coming from the left or right. You can be coming from any direction. So for something to be a boundary point, it has to be true that if you drew the tiniest disk around the point, there's some points that are exterior to the region, and there's some points that are interior to the region. And for this, what that means is that there always has to be a point that's interior, and there also has to be a point that's exterior to whatever region. And that's what makes something a boundary point. So for us, though, analytically, we're thinking about this as being just things that we can't, that are outside of our domain. So for this example 2, we have to find the limit at the boundary point. So it's clear that negative 4, 2 is a boundary point, because if you substitute negative 4 in for x and 2 in for y, you're going to get 0 in the denominator. Now, that's not the only boundary point. There are many boundary points, and they all would have to do with when x equals negative y squared, or when negative x equals y squared, however you want to think about it. But all of those are a boundary point. So it's not just one point. So when we were used to having functions like f of x equals something like, I don't know, like 1 over x squared minus 4, it's quite apparent that x can't be 2 and x can't be negative 2. But when we're dealing with R2, there could be a whole geometric structure that our function can't, that our function is not defined at. And again, when we think about boundary, it sounds like we're dealing with extremes, but this parabola, x equals negative y squared, could be right in the middle of a plane or something like that. So anyway, so when we're finding the limits at boundary points, it's just like what we did in Cal 1. You are trying, the first thing that you want to do is see if you can like factor to cancel some stuff. If you can, great. If you can't, the limit doesn't exist there. So for this example, we're going to rewrite this. And if we pay attention to the fact that we have a difference of squares. All right, so I'm just going to abbreviate limit because this is a lot to write. So we'll say the limit and x squared minus y to the fourth is going to factor to be x minus y squared times x plus y squared. And then we divide by x plus y squared. You know what, Mr. Moran, don't be lazy. Don't be a lazy mathematician. So x, y, and it approaches the point -4, 2. So we can see that we can cancel the x plus y squared, and we get the limit as x, y approaches -4, 2 of just x minus y squared. And so now if we substitute in -4 and 2, we're going to get -8. And so the limit when we approach in any direction. And so again, like in R2, all right, so we're going to just imagine that we're on the level curve for this function. So the point -4, 2 is over here. So we're in R2. So we're just in the XY plane. So the point R2 is here. When we say we converge to a point for a limit in at least three-dimensional space, what we're saying is that you can approach this point in any direction. You can come from any direction that you want, and the height that this function will be above the XY plane at that point is, well, in this case, below the XY plane would be -8. So when we approach a point in R2, you're coming at it from any possible direction. So we're used to like in single variable calculus, you would be concerned with something like this, where you only approach from the left or you only approach from the right. And the y value is determined by where you are on the x-axis. In R2, both x and y are interacting, so we are approaching in a circle. There's a radius of points that make this stuff true. And we'll see that when we talk about the two-path test in just a moment. So for the second example, same thing. If we substitute in 2 and 1 for x and y respectively, we're going to get 0 in our denominator. So we already know some tricks for dealing with square roots from Cal 1, so it's going to be kind of the same thing, where we multiply by the square root of x plus 2y plus 2, that's the conjugate, and we multiply by the square root of x plus 2y plus 2 in our denominator as well. So in the numerator, remember, anytime we multiply two conjugates, we're going to get the first term squared minus the second term squared. So we're going to get the limit as the point xy approaches to 1 of x plus 2y minus 4 over x plus 2y minus 4. And in the new and so then in our denominator, we still have the square root of x plus 2y plus 2. Now, conveniently, those two terms cancel. So we get, to avoid rewriting this, we're just going to say we substitute in 2 and 1 from here immediately. And so we get 2 plus 2 is 4. The square root of 4 is 2. So this is 1/4. All right, so now, again, boundary points, they function just like asymptotes or something like that in single variable calculus. If you can factor it out, the limit is going to be the limit in that simplified expression. If not, that may be what the two-path test is for. So, again, like in single variable calculus, for the limit to exist, it has to be true that the limit from the left is equal to the limit from the right. And those are easy to check. You just have to, if you have a function, you can use a value slightly smaller, and a value slightly greater than, and as you approach, if you get the same value, the limit exists. Again, if we're dealing with this point in space, but I can approach from any point in space, then there's an infinite number of ways that you can actually approach here. I can like approach in this direction, or 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 this direction. You get the point. So it's impossible to consider every possible path that you can take to show the limit does exist. The two path test tells you when the limit doesn't exist. And that's just going to mean you take two different paths to get to a point. And so now, again, we'll just project this down into the XY plane. When we talk about a path, what we mean is like you're taking some curve to get to the point. So like this frequently happens at the origin, and it's because you can always manipulate a function so that the limit could just be at the origin instead. So like say we have this point. Now there are a couple of ways you could go to the we can get to this point. One way is that we could just approach this point in a line. Now the line doesn't have to be unique. It can be this line. It could be that line. It really just needs to be some line of the version y equals mx, where just m is the slope. You could also like approach this point in a parabolic path, where if we have y equals x squared, then we'll say like mx squared. So we're approaching in parabolic paths to get to that point. All of the points could be of some parabola that get there. We can go that direction, this direction, that direction, or whatever, however you get to that path. So the point of the two path test is that if when you're approaching along two different paths and you get different limit values, the limit can't exist at that point. Because for the limit to exist, all of the limits, they have to converge to the same value. So showing that the two path test doesn't exist, it requires that we are slightly clever about how we choose our points. And so it's always the general principles that we'll talk about in class, but some of it is just based on how the function is structured. So for this next example, we need to show the limit doesn't exist using the two path test. So pay attention to when you have a sum, a product in your function, because that's kind of going to dictate what you have to do. So the first thing is, so we can first check this by suppose x equals 0. So we're approaching on the line x equals 0. So on the line x equals 0, that's just the y-axis. So the y-axis, that means that y can be whatever it wants, but x is 0. So if under the assumption that x is 0, the line x equals 0, then what we're doing is really just finding the limit as y approaches 0. And if x is 0, then this term disappears and that term disappears. So we would get 0 squared plus y squared over 0 squared minus y squared. And that's just going to give us the limit as y approaches 0 of y squared over negative y squared, which we know to be -1. So if we approach the point 0, 0 for this function on the y-axis, we get -1. That's going to mean that we get a level curve at -1. So now we could do the same thing, but we could do it for the x-axis instead. So now suppose that y equals 0. So y equals 0, we know again to be just the x-axis. So if y equals 0, then what we have is the limit as x approaches 0 of x squared plus 0 squared divided by x squared minus 0 squared, which is obviously 1. So we get two different values here. The limit doesn't exist. So we say something like by the two path test, I don't know why I capitalized 2, by the two path test, and then we'll even say using y equals 0 and x equals, these are lines, by the way, not us substituting in a particular value for x and y. These are lines. So by the two-path test using y equals 0 and x equals 0, the limit does not exist. And that is because we, again, got two different values. We got -1 when x was 0 and 1 when we were on the line y equals 0. So for this next example, we have the same thing, and we're going to the origin. And again, the reason we go to the origin is that you can always manipulate the function so that the point is approaching the origin instead. All right, so now we could try that same trick where, we could say something like, well, suppose y equals 0. Well, if y equals 0, then the numerator is going to be 0, and so would our denominator. Because then if x approaches 0, we get 0 minus 0. So now we know that 0 over 0, that's that indeterminate form that we can't actually work with. Now, in the previous problems, we were able to like factor and do some algebra to like cancel that stuff out. But we can't do that here because there's no way to suitably factor the denominator and cancel anything in the numerator. So what we can do instead is suppose we approach using any line of the form y equals mx, and the caveat is that m is not equal to 0, because then that's going to get us that horizontal line that we just established did not work. So as long as m isn't 0, so we can see from this function that if x goes to 0, this line is going to go to 0. And so we already know that. Like if we draw up here, we'll draw the xy plane, right? So we know that if I take a line, we'll just say m equals 1 for the sake of argument, that when x approaches 0, when x is approaching 0, y is also approaching 0. So that's going to be true for any line of the form y equals mx. When x goes to 0, y goes to 0. So what we're saying is the limit as x approaches 0 for y equals mx is equal to 0. Cool. So now that helps us maybe. We'll see what happens. So if y equals mx, then so we're going to erase that part so I can have some room to work. So if y equals mx, what we're actually finding is the limit as x, and since y equals mx, we just replace it with mx. So then as mx approaches the point 0, 0, we would have x times mx over divided by x squared minus mx to the fourth. And so in the numerator, we would get the limit as x approaches 0 of x squared m, and indulge me for a moment. So here we're going to get x squared minus m to the fourth, x to the fourth in our denominator. So now notice that we could factor out easily in x squared, and that will leave us with 1 minus m to the fourth x squared. So what we would get now is in our denominator, we would get x squared times 1 minus m to the fourth x squared. Now notice that we can cancel out our x squared here. So what we're left with is, now when x approaches 0, we're going to get m divided by 1 minus m to the 4 times 0. So we get m. Now again, m's not 0, so we know the limit isn't 0. That's important. So now so that's one path. We chose one path where we approach on a line. So now the other trick that we can use is pay attention to the powers that we have in our denominator. So if we could substitute something in for x that will give us y to the fourth, then we can probably like cancel some stuff out. Let's see what happens. So now if we approach along like a parabolic path, so now if y, nope. Oh, well, we could say, well, if y squared, well, we'll write it differently. We'll say if x is equal to some number times y squared. So now when y approaches 0, x is going to approach 0. Same principle. So now we're looking at the limit as my squared y approaches 0, 0. Now up here, notice that from this step to that step, we got rid of the second coordinate. And it's because when x goes to 0, that's going to go to 0 anyway. So kind of redundant to have it in the problem. It's fine if you do, but it's also fine if you don't. So this xy now turns into my squared and y, and that's still approaching the point 0, 0, because again, when y goes to 0, that x coordinate is going to go to 0. So now we replace x with my squared. We're going to have my squared times y divided by my squared minus y to the fourth. And that's going to give us the limit. Now, again, you can just drop the first coordinate because y is going to go to 0 for both. So the limit as y approaches 0 of my cubed divided by, so now we're going to get m in our denominator here, we're going to get we're going to get m squared y to the fourth minus y to the fourth, and we can factor that y to the fourth out. So we get y to the fourth times m squared minus 1. So we can obviously cancel out 3 of these, so we end up with the limit as y approaches 0 of m over what we get, y times m squared minus 1. And so now we have this problem where if y approaches 0, now m in m squared minus 1, that's a constant. So that part doesn't affect our limit. So now we can go back to single variable calculus for a moment. So if we approach 0 from the left, assuming m is positive, if we approach 0 from the left, we're going to get, this is going to approach negative infinity. If we approach 0 from the right, this is going to approach positive infinity. All that's going to tell us is that here, if we use this parabolic path, the limit doesn't exist. And so since the limit doesn't exist for if we approach along that path, but if we approach along the path y equals mx, we actually get a fixed value. That's enough for us to say the limit doesn't exist at that point, because we got a fixed value, a finite value of m, and here we got the limit does not exist. So we got 2 different limits by doing this process. So by the 2-path test, again, the limit doesn't exist. There's a lot of work to figure out that the limit doesn't exist. I should point out that the 2-path test does not show that the limit does exist. That's a lot of work for a multivariable function. So the last thing is the rules for continuity that we know from Cal 1. It's the same thing, but instead of a single coordinate, we have a point. So the function has to be defined at the point, the limit has to be defined at the point, and the limit as you approach the point has to equal the function value at that point. So we're not gonna show things are continuous. We want to talk about where functions are continuous. So for this next example, we want to say, well, where's this function continuous? So we know that individually these are polynomial-like functions. So this is continuous. The numerator is continuous everywhere. And If not for being in the denominator, this will be continuous everywhere. But we have to worry about where this equals 0. So x times y squared minus 4 is equal to 0. Two things have to be true. Well, x could equal 0, or y squared minus 4 equals 0. So y equals 2, or y equals negative 2. So the function is continuous. So total, we say f of xy is continuous when x is not equal to 0 and y is not equal to 2 or y is not equal to negative 2. So any point that doesn't have those as coordinates individually. So that's going to give that would be, so we can't have a point like 0, 1, and we can have a point like 3, 2, or something like that. So for any points that don't fit that description. So that's it. And so our last thing is for the logarithm. So now if we remember how the graph of the logarithm looks in 2D, it looks something like this. It looks like that. And so the input value is never 0. So that still has to be true here. This has to be strictly greater than 0. So what we need is x plus y is greater than 0. That's the same as saying x is greater than negative y. So if x was 3 and y was negative 2, then clearly 3 is greater than negative 2. Now, obviously, it's going to be true for positive values. So if I gave you the point like 3, 4, then that works out because 3 is greater than negative 4. So we would say something like continuous for all points x, y, with the condition that x is greater than negative y. So that means there's a point like 3, negative 7, that's not in our domain. It won't work because 3 is not greater than positive 7 because the negative of negative 7 is positive 7. All right, so that's our video on limits and continuity. We'll do a lot of practice with this in class. The two-path test is something that gives students trouble. Thanks for watching.